Hi there, this is Heath. Today's section is on spanning trees. Let's get started. Let G be a connected graph, but maybe not a tree. A spanning tree of G is a subgraph which is a tree and which includes every vertex of G. Let me show you an example. This graph here is not a tree. In order to be a tree, a graph has to be connected. This graph is connected, but the graph has to have no cycles. And this graph has cycles. And so this graph is not a tree. This graph down here in red is a spanning tree. It's connected. It has no cycles. And it includes all vertices in G. So I can get from every vertex to every other vertex along the spanning tree and never use these two edges here. That's what a spanning tree does. It connects the entire graph together, but doesn't finish off any of the cycles. Another definition here, a weighted graph is a graph with a function that takes every edge and gives it a real number, a non-negative real number called a weight that represents a cost in terms of money or time or some sort of cost associated with traversing that edge. This is an example of a weighted graph. This edge costs $95 to traverse, or $95 to build, or 95 hours to build, or some kind of units. There's a cost associated with this edge, and this edge is much more expensive than this edge down here. Okay? If I want to traverse around this weighted graph, I would like to avoid taking this expensive edge when these two edges are cheaper. These edges form a cycle, and I don't need all of the edges in the cycle to traverse this graph. And so my question is, can I find a spanning tree of minimum weight for this graph? Can we create a subgraph that allows for any node to get to any other node? Every vertex gets every vertex, but includes only the least costly edges. We're going to see two algorithms for solving this problem. One's called Kruskal's algorithm and one is called Prim's algorithm. Let's start with Kruskal's. We start out with no edges selected. We start out with no edges selected. And then we initialize the algorithm by choosing one of the least expensive edges in the entire graph. If there's a tie for the least expensive edge, we can choose any of them. So choose the least expensive edge. If there's a tie, choose any of them. And it doesn't matter which one, just choose one at random. And then we're going to add that least expensive edge to this set. As long as we still have some unreachable vertices, in other words, as long as we have not spanned the entire graph yet, choose a least expensive edge that extends the selected edges without creating a cycle. This is important because we're building a tree and trees cannot have cycles. And append it to the selected edges. When we are finished, once every vertex is reachable, we have a spanning tree. I'll show you an example on the next slide. So we want to find a minimal spanning tree for this graph. So we start out with this list of selected edges. And that list starts out being completely empty. I initialize with the cheapest edge I can find anywhere in this graph, and that's this weight right down here. This is the graph. This is the edge from C to D. And so I'm going to add CD to my to my selected edges. And so now this edge right here has been selected. Okay. I'm not finished yet because there are plenty of vertices that I cannot reach using just this edge. So now I look for the next cheapest edge. And the next cheapest edge, there is a tie. So we started out with the edge of weight 10. The next cheapest is 20, but there's a tie. When there's a tie, we can break the tie arbitrarily. I can choose either of these two edges. It doesn't matter. So I'm going to choose C to E. I choose that edge. Add that to my list. All right. I still can't reach every vertex, so I keep going. The next cheapest is the other 20. But I can't include this edge because it completes a cycle, and trees don't have cycles. But it creates a cycle. And so I cannot use this edge. And so I keep going. The next cheapest is 25. That's way up here. I'll add that edge. So now GH is in my list. The next is 30. That's down here. That's FG. I'll put that in my list. The next one is 35. That's here. That's B to G. And then 40. And that's down here. B to E. Okay, so far I'm just adding the cheapest edges I can find. The next cheapest edge is 45, but I can't add this because it would complete this cycle. 45 makes a cycle. And so I throw it out. The next edge after that is 50. And I will include 50. And at this point, every vertex is part of my tree. So I'll add AB to the list. And I don't need to look at 60 and I don't need to look at 95 because I finished the tree before I even got to those edges. Okay, it's not a hard algorithm. Start out with the cheapest edge, build up in order of weight, skipping over edges that finish a cycle. Here's another example. We start out with selecting edges. We start out selecting no edges, but then build our tree from this list. The smallest weight is 2, and so we'll include the edge from G to H. The next smallest edge is 3, that's up here from A to B. The next smallest edge is 4, and there are 2 edges of weight 4. I can pick whichever one I want to at random, so let's pick this one from G to C. It was tied with some other edge. So now the cheapest edge is still 4, and I can pick both 4s because they don't complete a cycle. So I'll also include FG. The next cheapest edge is 5. There's a tie. I'll break the tie arbitrarily. Let's say this time we're going to pick C to D. And there's a tie again. Well, now the next cheapest edge is 5, and I can pick it too because it doesn't finish a cycle. So B to C. The next cheapest edge is 6. That's down here. There was a tie. I could have picked either one. But I picked the one from D to E. At this point, every vertex is included in my tree, and so I stop. There would have been 2 correct minimal spanning trees for the graph because I stopped on a tie. And if I, instead of picking this edge, I'd picked this edge, I would have gotten a slightly different tree, but it would have the same weight. Excuse me. So now let's look at Prim's algorithm. Prim's algorithm starts out with a list of edges and vertices. And we begin by choosing any vertex. And then what we do is we choose a least expensive edge that connects to what we have built so far. That connects one selected vertex to one unselected vertex. And we proceed through this while loop until we have selected every vertex. This is a slightly more complicated algorithm, and after we go through a couple of examples, I'll talk about why we would sometimes want to use the more complicated algorithm. So use Prim's algorithm to find a minimal spanning tree for this graph. This is one that we looked at before. We start out with a set of selected vertices. And selected edges. And both lists start out empty. I initialize the algorithm by picking any vertex at random. And I'm going to pick G to start out this algorithm. Okay. So then what happens is I now pick the cheapest edge that connects G to some unselected vertex. So I have to look at this edge, and this edge, and pick the one that's the cheapest. And that's the edge to H. So pick a vertex at random, pick the cheapest edge that connects to what we've picked already. And does not create a cycle. And so in that case, this was 25. All right, so now we pick the next cheapest edge that connects to what we have up here. So that's either 30 or 35. 30 is cheaper, so we'll pick the 30. And that will be from F to G. And we have now selected vertices H and F. We selected H earlier. I just forgot to add that up there. Now I'm going to look at all of the edges that connect to this 3-vertex structure here. So I have to consider 35 and 95 and 45. But 35 is the one that's the cheapest. So we'll pick out 35. That adds B to the set of vertices and BG to the set of edges. So now I'm going to consider 50, 95, 45, 40, and 60. All of these edges that touch the structure we've built so far. The cheapest of these edges is 40. And so that will add E to the set of vertices and BE to the set of edges. And now we look at all of the edges that connect to the structure so far. And the next cheapest edge is 20. And I have a tie, so I can choose how to break the tie. This time I'll choose the one that goes straight down. That adds D to my list and DE to my list of edges. All right, now I look for the cheapest edge I can find. Now I can finally pick the 10 because I've hit this D. I can pick that 10. And so that adds C to the list, and it adds CD to the list of edges. And then I look at the cheapest edge that connects to this structure. 20 I can't use because it would complete a cycle. 45 I can't use because it would complete a cycle. And 50 I can use because that will extend the graph over to A and add AB to the list of edges. And now every vertex has been included in the graph. And so I have a tree. Why would we maintain a list of vertices and a list of edges when Crucicles just requires us to pick a list of edges? The simplest answer for that is that Prims has the feature of that the tree that we are building is connected at every step of the algorithm. And if we're physically building some kind of network and we don't have the resources and the money and the time to build it all at once, if we have to build it in stages, then Prims gives us a way of building the cheapest part of the network from some central node that is all connected, and therefore it is already functional even though it doesn't reach the entire graph. Whereas Crucicles can have a whole bunch of separately disconnected parts that don't talk to each other. And so sometimes Prims, the extra overhead, is worth it because you always have a connected network at every stage of the process. We'll do one more example using Prims. I start out with a set of selected vertices. And it starts out empty. Set of selected edges. And it also starts out empty. And I'm going to pick E for my starting vertex. So the first thing I do is I look at all of the edges that I can extend from E and pick the cheapest edge, but there's a tie. I could go up to D or down to F. So let's go down to F. It's not down to F, it's left to F, but that's okay. EF. And then I look at all of the edges that will extend the graph from here, including the 6 that I didn't include before, the 7, and the 4. I choose the cheapest of them, and that would be this 4 right here. That's from G to F. And that adds G to the list of vertices that we found. Then we look at all of the different edges that will extend the graph from where we have so far. Pick the cheapest one, that's the one from G to H. Keep going, picking the cheapest edge we can find. 3 is the cheapest edge, but it doesn't connect to anything we've built so far. So 4 is the cheapest edge that extends the graph, and that puts vertex C in our list. Then I have a tie between the two 5s. I'm going to take the one on the right. All right, that gets D onto the list. But the cheapest edge that extends the graph now is the other 5. So I'll go ahead and take the other one also. And that adds B to the list. And then finally, the cheapest edge that extends the graph now is the 3 that gets me over to A. And at this point, every vertex is included. And so I have a spanning tree, and I never had to consider these expensive edges 9, 8, 7, and 6. That's how Prim's algorithm works. Any questions? So if we wanted to implement this algorithm in software, we might want to come up with some technique for storing the graph. And one way to store a graph is in the form of an adjacency matrix. An adjacency matrix has a row and a column for every vertex, and it stores the weight of an edge between the pair of vertices. And 0 if there is no edge between the vertices. So let's create the graph from this adjacency matrix. I have 5 vertices. So I'll go ahead and plot down the vertices. Vertex 1 connects to 2, 3, and 4, but not to 5. Because there's a 0 here at 5. And the weights of these edges are 3, 5, and 1. Vertex 2 connects to 1, but we already have that one listed, along with 3 and 5. And this edge has a weight of 2, and this edge has a weight of 4. Vertex 3 connects to 1 and 2, which have already been listed, and then 4 and 5. 4 with a weight of 3, and 5 with a weight of 1. And then finally, vertex 4 connects to 1 and 3, which we've already included, and then 5 with a weight of 6. 5 should just be a check, connects to 2 with a weight of 4, 3 with a weight of 1, and 4 with a weight of 6. And so we could take this weighted graph and store it internally as an adjacency matrix. Adjacency matrices are easy. They're not hard to work with, but for a large graph, this can also require a large amount of storage. To store a graph with 5 vertices, we need to use 25 entries to do this. Storing n squared entries is not a very efficient way of doing this. So let's talk about a slightly more efficient way of storing a graph. Not slightly more, it's actually much more efficient. It's called the proofer sequence. But it only works for trees. Proofer sequences store trees only and not other more general types of graphs. So let's see how proofer sequences work. We start out with the vertices on the tree labeled in numerical order from 1 through n. They can be labeled arbitrarily on the graph. They don't have to be labeled, say, from the root down to the leaves. The order of the vertices doesn't matter, but we want each vertex to have a label. We start out setting the proofer sequence to be empty, and we find the leaf with the smallest label, call it V, and we, instead of adding V to the sequence, we add the parent of V, V's only neighbor. We add W to the sequence instead. Then we pluck the leaf off of the tree and repeat this process until we have just a single edge, and then we stop. Okay? We stop when we have one edge remaining in the tree. So we're going to generate the proofer sequence for this tree. The proofer sequence starts out empty, and I begin by looking for whichever vertex has the smallest value, whichever leaf has the smallest value on it. So find the leaf with the smallest value. 1 is the smallest value, but it's not a leaf, so we have to pick 2. We add whatever vertex 2 is connected to. So 2 is connected to 4. 4 is going to be the first number in my proofer sequence. And then pluck 2 from the tree. So now this entire edge is gone. Repeat the process. Find a leaf with the smallest value. It's not 1 because 1 is not a leaf. It's not 3 because 3 is not a leaf. It's 4. But we don't put 4 on the list. We put the neighbor of 4, which is 3. And this time we pluck the 4 off of the tree. Keep going. Find a leaf that has the smallest value. 3 and 1 are not leaves, so the smallest leaf is 5. And its neighbor is 1, so I'll add a 1 to my list, and then pluck this leaf from the tree. Now I only have 2 leaves left, 6 and 7. 6 is smaller, so I will take the 6, add its neighbor to the list, which is 3, and then cross the 6 off. Here's what I have left, just the line segment from 3 to 1 to 7. 3 is now a leaf, and it's smaller than 7. And its parent is 1. And now I will pluck that leaf off of the tree. And when I have one edge left, and so I took this graph that had 7 vertices, and I'm storing it using only 5 values. I'm actually storing it using fewer values than vertices. But from that list, 4, 3, 1, 3, 1, I can recreate the entire graph. And we'll do that in just a moment. Here's how we convert the sequence back into a tree. We create a list of all of the vertices, 1 up through k plus 2. The list of vertices will have 2 more entries in P. Like in this example here, we had 7 vertices, but only 5 numbers in the list. We figure out what the size of the list is, add 2, and that's how many vertices we're going to have. We will start with an empty graph, and then find the smallest number in this list that does not appear in the proof of sequence. And then take the first number that's in the proof of sequence. And we will connect an edge from vertex J to vertex K. And repeat this process. Let me show you. It's easier to show you than to go through the description of the process. My proof of sequence was 4, 3, 1, 3, 1. We're going to rebuild the graph from the last example. This has 5 entries. That's a 5. And so we have 7 vertices. 1, 2, 3, 4, 5, 6, and 7. We find the first number in the list L that does not appear in P. What's the smallest? In L that's not in P. And the answer is it's not 1 because 1 shows up in P, so it's 2. We match that number to the first number in the list. First number in P would be a 4. And so I draw an edge from vertex 2 to 4. And then I cross off the 2, I've used it up now, and I cross off the 4, I've used it up now. Okay, repeat this process again. What's the smallest number in L that's not in P? 1 is in P, 3 is in P, 4 is not in P because I've crossed it out. So we map the 4 and the 3 together. The smallest number in L with whatever number comes next up in the list. So 4 connects to 3. And then I have used up the 4 and I've used up the 3. Let's keep going. Smallest number in L that's not in P. 1 is in P, 3 is in P. 5 is the smallest number that's in L but that's not in P. And 1 is the next number in the list of P. So I need an edge that goes from 5 to 1. Well, that's not connected up here, but that's all right. 1 to 5. Cross these out. All right, smallest number in L that's not in P. 1 is in P, 3 is in P, 6 is not in P. So 6 and 3 connect together. And I cross them out. Smallest number in L that's not in P. 1 is in P. 3 is no longer in P because all the 3's have been crossed out. And so 3 and 1 will connect together. And then those get crossed out. And then finally, the end step. Because there were 2 extra vertices in L that are not in P. We have used up everything in P, but we still have these 2 vertices left. We'll connect them together. I'm going to put an edge from 1 to 7. And so this is my graph, and this graph is isomorphic to this graph here. Okay. Last 2 vertices in L, we connect them together. We'll do one more of these, and then we'll wrap up. Let's try constructing this tree. 1757771. 175771. I think I said that wrong. That has 6 entries. I'll add 2 to that number. And so I need 8 vertices in my list. All right. I find the smallest number that shows up in L but not in P. And that will be a 2. And then I just read off the first number in the list P. And that means I have to connect vertex 1 and vertex 2. And then cross them off, and they have been used. Then I find the smallest number in L that doesn't show up in P. 1 shows up, but 3 doesn't. So I need to connect 3 and 7 together. And those connect together, and I cross them off. Smallest number in L that's not in P is a 4. 4 connects to 5. I'll put them over here. And I cross them off. This time 5 doesn't appear in P anymore because it's been crossed out. So 5 connects to 7. Oh, I did not place this very well, but I'll put the 5 to 7 around here. Cross them off. 6 is now the smallest number on the list that doesn't show up in P. So 6 and 7 get connected together. Now 7 no longer appears on the list, so 7 is the smallest number. And 7 connects to 1. And then those 2 get crossed off. And once I have no entries left in P, I still have 2 entries that are left over in L. I will connect them together also. And so 1 connects to 8. And I could redraw that to try to make it look more tree-like, but this is the tree that I have built from this proof of sequence. All right. Y'all have a great weekend. Take care.